Hi guys, this is going to be a new type of instructional video where there's going to be questions embedded into this video, and then you have to enter the answers, and then I check to see if you answered them correctly or not. So it is very advanced in our technology endeavors, and I just hope and pray that it actually works. Okay, so I'm going to take some time to go through the notes. You guys copy it down in your own notebooks while I go, and I will pause it at times just so you might hear some rattling or air conditioning going, because I am stalling so you have enough time to write it down. There is this cool thing called the pause button that if I'm going too fast you can pause the video and take your time, write it down, and then go from there. Okay, so we are talking about limits at infinity, so that's as x goes left forever and as x goes right forever. Forever to the negative direction and forever to the positive direction. I threw this vertical asymptote in there just to be on the safe side, that as x approaches a value, an a value, right, that our limit is going to infinity. That creates a vertical asymptote. So as my left-hand limit is approaching a, the y's are going up, up, up. And then over here, sorry, did I say right-hand limit? I meant left-hand limit. And then my right-hand limit's approaching a, the y's are going up, up, up. So it does create a vertical asymptote. As x's are approaching a, the y's are going to infinity. Next, horizontal asymptotes is where this section 2.6 comes from, and we did discuss this earlier with our little mean girl slide there, right? The limit does not exist. Well, in this case, as x approaches positive and negative infinity, that means x's are going to the left forever or x's are going to the right forever. Our y value is approaching a specific number. So in this case, as the x's are going out this way, the function is getting closer and closer to 0. 0 is a number, it is a value, so it creates a horizontal asymptote. As x's are approaching infinity going to the right, the y's are going towards 0 once again. So if the x's are going really big and the y's are going to a number, it does create a horizontal asymptote. So something to think about, I could have put another portion of this graph coming this way through the middle. Okay, it's still going to be a function, but notice how in the middle of the graph, this graph is crossing through the x-axis, and it means that it is crossing through the horizontal asymptote at y equals 0. It's okay if the function crosses through at the middle of the graph. It's just far to the right and far to the left at negative infinity and positive infinity, or close to it, because could you ever actually get to infinity? Good question. That it won't cross over the horizontal asymptote. Vertical asymptotes, no, it won't pass the vertical line test to be a function anymore, so those will never cross over. Horizontal asymptotes, you're allowed to cross over in the middle of the graph. So the theorems that we need to remember here, it's pretty intuitive, but as x goes to positive infinity, if you have a rational function like this one, 1 over a huge number to a positive number, a rational number, right? So you have a big number to a rational power, it's still going to be a really large number in the bottom. But if I divide 1 by 100, 1 by 1,000, 1 by anything, let me go over here for a sec and flip it. If I do 1 divided by 100, oh, it gives it to me in fraction form. There we go. And then I can say 1 divided by, I don't know, a lot. Put it in decimal form. Oh yeah, look at that. The more zeros you put in the denominator, the bigger the number goes in the bottom, the more decimals you have, or the more zeros you have after the decimal. So that is getting really, really close to 0. So it doesn't matter if you're plugging in a positive x going to positive infinity or a negative x going to negative infinity. As long as r is rational, that means that you will have this limit go to 0. We are going to use that once we get to the calculus method. We've done all of this already in pre-calculus by finding the horizontal asymptotes. Horizontal asymptotes is going to be the same as the answer to solving these limit problems. So I'm just reviewing for you. If the degree in the numerator, you have a fraction, degree in the numerator, the highest exponent on the top, is bigger than the degree in the denominator, this d stands for degree in the denominator, there is no horizontal asymptote. right? So then you have to think, well, there's a slant asymptote. We haven't been really big on slant asymptotes, but I did graph one for you. You can see this is a rational function. The degree on top is 2, the degree on the bottom is 1, so the degree on top is bigger. There is no horizontal left and right, asymptote. It is a slant asymptote, and that slant asymptote is bounded about this line x minus 2. Now if you're intrigued on how to come about that, I'll be more than happy to show you the algebra, but I'm just saying that there is no horizontal asymptote if the degree on top is bigger. But if I did say put a limit right in front of that as x goes to infinity, you can follow this x going bigger and bigger and bigger. Where's my graph going? Oh, well, the graph is going up, 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 positive. If I check my graph going to the left, x's are going to the left, what is the y values doing? This y value looks like it's pointing down to negative infinity. So this is a good time for a check. If the degree in the numerator is bigger than the degree in the denominator, your answer to these limit problems will either be positive infinity or negative infinity. Next, number 2, degree in the numerator turns out to be smaller than the degree in the denominator. You're going to have a problem where the horizontal asymptote will come out to be 0. So if I wanted to graph this now, whoops, get rid of that, and then tab, 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 why aren't you working? There we go. Change this down here to a third power. Let's see if that works. You can see as x's are going to the far, far right, what are the y's doing? It's going so close to 0. Check over here on the left-hand side, right? As x's are going to negative infinity, the function is going closer and closer and closer to 0. So either left or right, the function will go to 0. Remember what I said about horizontal asymptotes? It's okay to cross at the middle of the graph. Oh, there's one that it crosses the horizontal asymptote. Wow! All right, so I showed you the first two. Now the last one, degree in the numerator is equal to the degree in the denominator. You're going to have to take the lead coefficient, so the number in front of the highest exponent, and divide it by the lead coefficient, the number in front of the highest exponent in the bottom. Your answer will be that lead coefficient over the lead coefficient. Let me show you an example of that one. Let's change it to 2, this to a 3, see if that works. Ooh, and then I'm going to also say, because the degrees are the same, I take the coefficients in front, so that's 2 over 1. So I'm going to just show you y equals 2. See how that doesn't cross through, right? It goes both ways right along that y equals 2. And we're looking as x goes to positive infinity and as x goes to negative infinity. So 3 different cases that we can use in order to find these limits. But it's the same rules that you already took from pre-calculus. Okay? The calculus method is by using that same theorem. Oh, I should probably put a All right, calculus method says we're using that same theorem that we were showing you on the last page, this one right here, that as x goes to either positive or negative infinity, 1 over that large number will always go to 0. And you can use this little rule up here to know why again, because the degree on top is 0. Degree on the bottom, rational number, right, it's going to be bigger than that. So that means that my answer will be 0 as well. But anyways, you're going to divide through by the largest degree in the denominator, and then you're going to use that portion. Anytime that you see 1 over x to some power, you're going to make that portion go to 0, and then you're going to simplify what's left over. Okay, so I'll show you both methods. You can choose which one you like better. Personally, I do like the pre-calc method. There is a couple problems where you can't use the pre-calc method, so you will have to use the calculus method, and that's why I'm showing you both. So here's an example. Pre-calc method, pretty fast. Degree on top is 2, degree on the bottom is 2. So what case is it? Yep, that is right. It is case 3, where you just take the lead coefficient over the lead coefficient. So my answer to this limit is the same as the horizontal asymptote, which would be 3 over 5. Now, if that's the pre-calc method, there's not much work to be shown. My answer will be 3 over 5 once I do it the other way. But the other way said that we're going to take the largest degree in the denominator. So that turns out to be x to the second power. I'm going to divide the top by x to the second, and I'm going to divide the bottom by x to the second. So I write the limit as x goes to infinity of 3 over x squared divided by x squared. So every single term on top needs to be divided by x squared. So the x squared in this first term gets canceled out. X over x squared, 1x is left. And then minus 2 over x squared, nothing cancels, so both of them are left. And then I divide 5x squared over x squared, leaves just the 5. 4x over x squared is a 4 over x. And then plus 1 over x squared. Now that rule we talked about, when you have a limit as x approaches infinity of a fraction, all of these guys are fractions. So all of these guys are going to be going until 0. So if you think of those as zeros, 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 and zeros, what's left of this equation? Well, there's only a limit as x goes to infinity of 3 over 5. 3 over 5 is a horizontal line, so no matter how far out you're going, it will always get to 3/5. Which way do you like better? Me too. All right, so the next one, if I use the pre-calc method, I'm going to take, wrong way with my pen, take the exponent on top, the exponent on the bottom, which is a 1. Now the degree in the numerator is bigger than the degree in the denominator, right? If that's the case, it's a slant asymptote. It's not a horizontal asymptote. And then you have to decide, shoot, is it going to negative infinity or is it going to positive infinity? Well, in this case, we're going to have to see what kind of factors are going about here. So if I play around with it, it's hard to tell with plugging in a negative infinity which one's going to be big. Well, I guess yeah, it would be too hard to tell. So I'd rather write it in factored form. Okay, I know my answer is either going to be positive infinity or negative infinity. From my graph, if you want to reverse it a little bit, it did go to negative infinity, but I'm going to show you how they got that. So if I factor out, multiplication is always easier to tell which way the function's going if it is in factored form. So now if I put in a negative number in front, it is going to be negative. If I put in a negative minus a negative, it's another negative. Okay, and then on the bottom, a negative plus 1, that's not going to change much. If I count the number of negative signs, the whole thing is going to be negative. So I know my answer is going to negative infinity. If you had an even number of negative signs, then you're going to say your answer is going to positive infinity. Okay, so that's just how you tell the difference between the two. Always put it in factored form before you can tell, is it going to be negative or positive. Good. You guys try this one. Oh, no, you can't try this one. I threw in a wrench to your bicycle. All right, so with this one, we can't use the pre-calc method. The pre-calc method doesn't work because I don't know what the degree on top is. It's inside of a radical equation, or expression, I should say. So what I'm going to do is use the calculus method. Calculus method says divide through by the largest degree in the denominator. So that happens to be the x squared. What you do to the bottom, you have to do to the top. But the problem is I can't put an x squared inside of this radical because x squared and the square root of x squared are not the same function, right? So we do want to divide through by something that is equivalent to x squared. So think of what number can I put inside of this radical and make it equal to x squared. That's right. Hopefully you got it right. If I put in an x to the 4th and I simplify the square root of x to the 4th, it will be the same, equivalent as x squared. So I'm going to rewrite this as the limit as x goes to infinity of the square root. I'm putting it big because I still have to divide through by that x to the 4th. 16x to the 4th, that doesn't change, divided by x to the 4th, plus 2x over x to the 4th. But we still have on the bottom, we're still dividing through, the bottom is not in radical form, so I can divide everything through by x squared. Whew, a lot of talking. So now once I sent through, this x squared got put inside of the radical by making an equivalent form, right? X squared is the same as the square root of x to the fourth. Now I can go through and simplify. And I get x4 over x4, which is going to be 16, plus one of the x's cancels with one on the bottom, leaving 2 over x. And then I get a 2 plus 1 over x squared. Okay. Same rule as before. If you ever have an x on the bottom, that whole thing goes to 0. That whole thing goes to a 0. So I don't need those terms anymore because I'm plugging in a big number to a denominator. 2 over a big number is a very small decimal. Remember, limits are what is x approaching. So once I get rid of those guys, goodbye, goodbye, I'm left with the square root of 16 over 2, which is the same as 4 over 2, which is the same as 2. So I got my answer to be 2. On the next problem, we are asked some certain graphs. Okay, can you please graph that? And then I will show you how. All right, between these these 4 graphs, I want you to tell me which ones are going to produce a vertical asymptote and which are going to produce a horizontal asymptote. Good. As x approaches a number, and y's are going to infinity, right? That means the y's are going either direction. That one would produce a vertical asymptote. So these 2 are vertical asymptotes. And then as x goes to infinity and y goes to a particular number, you're going to be producing a horizontal asymptote. Try to draw it out. It really does help. Okay, so these 2 would be horizontal asymptotes. From here to graph it, I like to actually along the 0 mark. As x's are approaching 0 from the right, our y values are going up forever. Now I don't know if it's going to really hook like that or not, but it is going to go up forever. And then as x's are approaching from the left-hand side, the y's are going down forever. So I took care of those 2. Now over here, as x's are going to the right forever, y's are going to 1. So here's my horizontal asymptote at 1. I'm not sure which side of the graph that's going to be on. It's up to you to decide. And then as the limit as x approaches negative infinity, y's are going to negative 1. So that's going to be a horizontal asymptote out here. Once again, why didn't I do the horizontal asymptote all the way across the graph? Because your function can cross in the middle. Yes, it can. And then f of 1 equals 2, that will always create a closed dot. So 1 up 2 is going to be a closed dot. So now it's just connecting your function however you want. So if you want this guy to go over and then out, totally fine. And then this guy, if you don't want it to cross through that dot, you could do an open dot right above it because you're pretty ingenious like that. And then it would go out forever that way. Okay, it's up to you. If you wanted it to go through the dot, totally fine. But I just want to let you know that yes, it still passes through the vertical line test because this is the only closed dot. The other one's open right above it. Good job, guys. We're almost done.